Hello everyone. So I'm back again, and it's been quite some time since I last uploaded, particularly because now my college has started and I have a lot of workload. But it is what it is. So we were covering this wonderful book by Michael Nielsen. We are currently on chapter 3, which dealt with how you can improve your neural networks. And now we're going to look at we had a look at many approaches to minimize the cost function, and now we're going to look at some other ones. So for the rest of the approaches, you can either go ahead and read the book, or you can just watch the previous video, anything which you prefer. Alright, so many other approaches to minimizing the cost function have been developed, and there isn't a universal agreement on what is the best approach. So, as you go deeper into neural networks, it's worth digging into the other techniques, understanding how they work, their strengths and weakness, and how to apply them in practice. Of course, makes sense. You cannot have a fit-all solution for all the different types of tasks which you can possibly have, right? Alright, so a paper I mentioned earlier introduces and compares several of these techniques, including conjugate gradient descent and the BFGS method. Uh, See also the closely related limited memory BFGS called LBFGS. Okay, this sounds quite cool. Another technique which has recently shown promising results is Nesterov's accelerated gradient technique. I'm sorry if I butchered that name up, which improves on the momentum technique. However, for many problems, plain stochastic gradient descent works well, especially if momentum is used, and we'll stick to stochastic gradient descent through the remainder of the book. So on a basic level, SGD is still the way to go for us. But as the author rightly pointed out, when you deal with more and more complex problems, then it might be worth looking into ways to minimize the cost function. Maybe that is the way to get that extra squeeze out that extra 1% minimization. All right. So other models of artificial neuron. So up to now we've built our network using sigmoid neurons. In principle, a network built from sigmoid neurons can compute any function, of course. In practice, however, networks built using other model neurons sometimes outperform sigmoid neurons. Depending on the applications, network based on such alternate models may learn faster, generalize better, etc. etc. Right. So perhaps the simplest variation is the TANH, produce TANs. I don't know what the author is trying to uh, imply here, but I pronounce it as TANH, or the hyperbolic tangent. So this neuron, which replaces the sigmoid function by the hyperbolic tangent function. The output of the tangent neuron with input x, weight vector v, and bias b is given by this. Of course, you've just replaced the activation. So where tan h is this? It turns out it is very closely related to the sigmoid neuron. To see that, this is the formula for the hyperbolic tangent. So you see some reminiscence of sigmoid, because sigmoid was 1 over 1 plus e to the negative z, right? So you see there are e to the z terms here as well. So with some algebra, and I leave this up to you to verify, you can show that the sigmoid of z is 1 plus tan h of z by 2, right? So there's a linear relationship between the two. That is, tan h is just a rescaled version of the sigmoid, and you can see that graphically as well. So it has the same shape as the sigmoid, just it lies between negative 1 to 1, and center is at 0. One difference between tanish neurons and sigmoid neurons is that the output ranges from -1 to 1, not 0 to 1. The This means that if you're going to build a network based on tanish neurons, you may need to normalize your outputs, and depending on details of your application, possibly your inputs, right? Because if your output is, say, here, somewhere here, it might not make sense for your the output in your context to be negative, right? Or in your application area. So you might have to do something similar to sigmoid. A network of tanish neurons can in principle compute any function ranging from -1 to 1. Furthermore, ideas such as backprop and SGD are as easily applicable, right? So there are some technical caveats for both tanish and sigmoid neuron, as well as for ReLU, discussed below. However, informally it's usually fine to think of neural networks as being to approximate any function to arbitrary accuracy, right? So you need to prove this. This is quite simple actually to prove. You could just substitute uh, z over 2 instead of z here and solve the equations, you'll see you'll get a z over 2 in the denominator, then you'll get a multiplication, they'll add up, and z over 2 in the denominators get cancelled out and so on, and you'll get the right output. Alright, so which type of neuron should you use in your network, the tanh or sigmoid? The answer is not obvious. However, there are theoretical arguments that some empirical evidence to suggest that tanh sometimes performs better. So you can have a look at these papers to see that. So let me briefly give you a flavor of one of the theoretical arguments for tanh. Suppose we're using sigmoid neurons, so all the activations in the network are positive, right? So let's consider the weights W, J, K, L plus 1. So this is the weight connecting the the kth neuron in the lth layer to the jth neuron in the L plus 1th layer. Jth neuron, yeah. The rules for back propagation. Oh, I shouldn't have done that. Um, right, I was here. So this show tells us that the associated gradient will be this, right? Because the activations are positive, the gradient will be of the same sign as the error in the particular neuron. This means that if this error is positive, then all weights will decrease, and if it's negative, then all weights will increase. In other words, all weights to the same neuron must either increase or decrease together. So that's a problem, since some of the weights may need to decrease and some may need to increase. That can only happen if some of the input activations have different signs. That suggests replacing the sigmoid by an activation function such as tanh, which allows both positive and negative activations. Indeed, because tanh is symmetric about 0, we might even expect that, roughly speaking, the activations in hidden layer would be equally balanced between positive and negative. That may that would help ensure that there is no systematic bias for the weight updates to be one way or the other. So that's a really good point. Maybe you don't really want all the weights to increase or decrease, and at that point, the sigmoid may be causing more of an issue than becoming a solution, right? So how seriously should you take this argument? While the argument is suggestive, it's a heuristic, not a rigorous proof. Perhaps there are other properties which compensate for this. So indeed, for many tasks, TANF is found to be empirically only a small or no improvement. Unfortunately, we don't have a hard and fast rule to know which neuron type will learn fastest or give the best generalization. So another variation is the ReLU, where which is also known as the rectified linear neuron or rectified linear unit. The output is just take the maximum of wx plus b and 0. So if wx plus b is negative, you get a 0, and if it is greater than 0, then you get a linear line, right? So obviously such neurons are quite different from both sigmoid and tanh. However, like the sigmoid and tanh, ReLU can also be used to compute any function using SGD and backprop. So, what should you use a ReLU instead of when should you use it, right? This is like a great question. So, because this looks so much different than the functions which we are used to seeing. They are smooth, they curve out at the end, but this is like a totally different thing. So when should you use it? So some recent work of image recognition has found considerable benefit in using ReLU. However, as with TANH, we don't yet have a really deep understanding of when exactly ReLU units are preferable. To give you a flavor of some of the issue, recall that sigmoid saturates near 0 or 1, right? But as we had seen, the sigmoid prime term causes this. Tanh neurons also saturate by similar problem. By contrast, increasing the weights will never cause it to saturate because this is a linear function, the ReLU one, and so there's no corresponding learning slowdown. On the other hand, when the weighted input to the ReLU is negative, the gradient vanishes, and so the neuron stops learning entirely. These are some issues that make it non-trivial to understand why ReLU performs better, right? And these are some papers which have been linked. This paper in particular I've read, the AlexNet paper. They used the ReLU activation and got overwhelmingly better results than the previous state of the art, creating the new state of the art, and led to an entire revolution in this field. And several great papers came out after this. Alright. So I've painted a picture of uncertainty here, stressing that we do not yet have a solid theory of how activation function should be chosen. Indeed, the problem is harder than I have described, for there are infinitely many possible activation functions, which is the best for any given problem. What will result in a higher or faster learning rate? What will give the highest test accuracies? So I'm surprised how little really deep and systematic investigation has been done of these questions. Right. So ideally we'd have a theory which tells us in detail how to choose our activation functions. On the other hand, we shouldn't let the lack of a full theory stop us. We have powerful tools already at hand and can make a lot of progress with those tools. Very true. Through the remainder of this book, I'll continue to use sigmoid neurons as our go-to neuron since they are powerful and provide concrete illustrations of the core ideas about neural nets. But keep in the back of your mind that these same ideas can be applied to other types of neurons and on and that there are some advantages in doing so. Right. So okay. So on stories in neural networks. Let's just read this. I don't really know what this is about. So, question: how do you approach utilizing and researching ML techniques that are supported almost entirely empirically as opposed to mathematically? Also, in situations, what situations have you noticed them fail? All right. So, you have to realize that the theoretical tools are very weak. Sometimes we have good mathematical intuition for why a particular technique should work. Sometimes our intuition ends up being wrong. The question becomes how well does my method work on this particular problem, and how large is the set of problems on which it works well. So this is answered by Jan LeCun. He was one of the authors of the Linnet paper, and which was one of the first MNIST classifying papers. And this was a this is a great answer, to be honest, because our intuitions are wrong many a times. I just had a very bad day with my intuition in a question based on probability because intuition often deceives us. So the question is, how well does your method solve your particular problem? And in the larger scheme of things, how many problems can your particular method solve? So once attending a conference on the foundation of quantum mechanics, I noticed what seemed to me a most curious verbal habit. When talks finished, questions from the audience often began with, I am very sympathetic to your point of view, but so and so. Quantum foundations was not my usual field, and I noticed this style of questioning because at other scientific conferences, I'd rarely or never heard a questioner express the sympathy for the point of view of the speaker. True. I haven't ever heard such things. At the time, I thought the prevalence of the question suggested that little genuine progress was being made in quantum foundations, and people were merely spinning their wheels. Later, I realized the assessment was too harsh. The speakers were wrestling with some of the hardest problems human minds have ever confronted. Of course, progress was slow, but there was still value in hearing updates on how people were thinking, even if they didn't have unarguable new progress to report. True. So so this is quite self-explanatory. I don't need to like explain this. You may have noticed a verbal tick similar to "I am very sympathetic" in the current book. To explain what we are seeing, I've been falling back on saying heuristically so and so, or roughly speaking so and so, following up with a story to explain some phenomenon or other. These stories are plausible, but the empirical evidence I've presented has often been pretty thin. If you look through the research literature, you'll see that stories in a similar style appear in many research papers on neural nets, often with thin supporting evidence. So, what should we think about these such stories? In many parts of science, which deal with simple phenomena, it's very possible to get solid, reliable evidence for a general hypothesis. But in neural networks, you have tons of parameters and hyperparameters and complex interactions. So it's difficult to establish general statements. True. So understanding neural networks in their full uh, generality. What's happening to me? Why can't I pronounce this? general Generality, right, in the full generality is a problem that, like quantum foundations, tests the limits of the human mind. Instead, we often make do with evidence for or against a specific instance of a general statement. As a result, those statements sometimes later need to be modified or abandoned when new evidence comes up altogether. That is quite a valid approach. So one way of viewing the situation is that any heuristic story about neural networks carries an implied challenge. For example, the statement I quoted earlier explained why dropout works. This technique reduces complex co-adaptation of neurons since a neuron cannot rely on the presence of particular other neurons. It is therefore forced to learn more robust features that are useful in conjunction with many different random subsets of the other neurons. So this is a rich proactive statement, and one could bring a fruitful research program entirely around unpacking the statement, figuring out it is true, what is false, and needs variation and refinement. Indeed, there is now a small industry of researchers who are investigating dropout and many variations, trying to understand how it works and what its limits are. And so it goes just as with other papers, other heuristics we've discussed. Each heuristic is not a potential, just a potential explanation. It also brings about a set of challenges. Of course, there is not enough time for a single person to investigate them all of these explanations in depth. It's going to take decades for the entire community to get evidence-based theory of how neural networks work. Does this mean you should reject heuristic explanations? No, totally not. In fact, we need these heuristics to inspire and guide our thinking. It's like a great age of exploration. The early explorers sometimes explode, and sometimes on the basis of wrong beliefs. Later, those mistakes were corrected as we filled in our knowledge of geography. When you understand something poorly, as the explorers understood geography, and as we understand our neural nets today, it's more important to explore boldly than it is to be rigorously correct. True. The far you venture, the more ideas you get in every step of thinking, and so you should view these stories as a useful guide to how to think about neural nets while retaining a healthy awareness of the limitations of such stories and carefully keeping track of just how strong the evidence is for any given value of reasoning. Put another way, we need good stories to help motivate and inspire us, and rigorous in depth investigations in order to uncover the real facts of the matter. So, this was a great read, to be honest, as are all the chapters of this book. This is simply amazing. So, I guess now we have these three left, right? Is the last chapter also chapter? Yep. And also the appendix. Yep. This seems quite interesting. So again, I'd like to apologize because there's like no way I can make another 15 parts at the same pace. So the pace might deteriorate. I might do some other things as well in between. But I believe that I will, at some point in the future at least, finish this series. So thank you everyone for tuning in. See you again next time.